term high-speed LAN is open for interpretation as to what is considered high speed. The general consensus is that this term refers to LANs with baud rates that are at least greater than what can be achieved through a serial RS-232 port found on a common desktop computer. There are many high-speed LAN technologies on the market today, with some being closed and others open. It's also generally accepted that Ethernet is the standard high-speed LAN technology at the physical through network layers. Over the past decade, there have been many advancements in Ethernet LAN hardware, resulting in high-quality, robust, and multi-vendor compatible hardware, readily available almost anywhere in the world at relatively low cost. It then follows that larger industrial and utility power applications have already migrated from older proprietary RS-232 and RS-485-based LAN technology to Ethernet, or are in the process of doing so. Over the years, several physical standards have evolved. The modern standards support full duplex Ethernet, while the older standards support only half-duplex operation. By far, the two most popular physical layer standards are 10100 base T and 10100 base F. Both support full duplex operation, each with its own advantages, and so it will be these two physical standards that we'll examine. The most common electrical standard today is 10100 base T. The 10 refers to the operating baud rate of 10 megabits per second, while 100 refers to a baud rate of 100 megabits per second. Most new equipment can operate at either baud rate, and so the designation 10100 has evolved to identify this capability. The term base stands for baseband, which means that the entire bandwidth of the LAN is used to transmit one signal. The T stands for twisted pair, which means the transmitter and receiver use separate pairs of wires for a differential signal, with the wire pairs being twisted together. Let's start with the configuration of the communication cable itself. The cable consists of 4 pairs of wires terminated in RJ45 connectors. The maximum length of the cable is 100 meters. Only pairs 2 and 3 are required for 10 megabit operation, while all 4 are required for 100 megabit operation. Having said this, most twisted pair cables are assembled with all 4 pairs. The cable pin connections can be one of 2 configurations. The first is called a straight-through cable, and the second is called either a crossover or patch cable. As per standard, each of the wires within the cable has the following color code regardless of whether the cable is straight-through or crossover. For wire pair 1, one wire is white with blue bands, while the other wire is blue. For wire pair 2, one wire is white with orange bands, while the other wire is orange. For wire pair 3, one wire is white with green bands, while the other wire is green. And for wire pair 4, one wire is white with brown bands, while the other wire is brown. The straight-through cable wiring is used to connect an Ethernet device to a switch or hub. The patch or crossover cable is used to establish a point-to-point Ethernet LAN between 2 Ethernet devices. The 10100 base T topology is a star topology, where each device on the Ethernet LAN branches out from a central switch or switches that have been connected together to form the backbone of the network. The port that connects one switch to another is often called the uplink port, and with many switches, the uplink port can operate at much higher baud rates than the standard ports. The connection of several higher-speed uplink ports to produce a higher-speed path between switches is often referred to as a backbone. The maximum length of cable between a device and the switch is 100 meters. All components used in a 10100 base T LAN should be rated with the Category 5 enhanced level of quality assurance. 2 of the major Ethernet network components are hubs and switches. You can think of either a hub or a switch as a big data manifold with connections for devices and other switches or hubs to exchange data. This means the data can flow to any device connected to the switch. Hubs and switches are microprocessor-based, and so many switches have configuration software to optimize the LAN's performance. These types of switches are called managed switches. Other switches have default configurations with little or no configurable features, which are called unmanaged switches. There are many advantages of a switch over a hub. Hubs just transfer information from one port to all other ports. Switches, on the other hand, can learn the location of specific devices and route messages to them, thereby reducing data traffic on the network. Switches also have the capability of buffering messages, which eliminates collisions on a full duplex Ethernet LAN. Let's take a closer look at this feature. Within a full duplex Ethernet LAN, all components can support simultaneous transmission and reception of data. For example, if the green and blue Ethernet devices transmit a message onto the Ethernet network at the same time, one of the messages will be buffered at the switch, and the other message will be passed through to the other ports. Once the blue message has been transmitted, the switch will send the green message automatically. Given that the maximum size of an Ethernet data packet is 1.5 kilobytes, even at a transmission rate of 10 megabits per second, the delay is negligible. If the switch were replaced with a hub, both messages would collide at all ports. This is normal for a half-duplex Ethernet LAN, and in such a case, both messages would eventually get through all ports using a collision detection mechanism, which is built into the Ethernet layers, but there would be additional delays. In recent years, the filtering and buffering advantages of switches have increased their demand, reducing manufacturing costs to be comparable to that of hubs, and as a result, many vendors are no longer offering hubs. The following 10100 base T lab has been divided into two parts. The first will demonstrate how to interconnect a 10 base T Ethernet LAN and an RS-485 LAN. We will be using the GE MultiNet to allow masters on the Ethernet LAN to communicate to SR relays on the RS-485 LAN. In the second part, we will demonstrate how to integrate the universal relay into the Ethernet LAN. The equipment required for this lab will include a computer with Windows 2000, NT, or XP, and a 10100 base T Ethernet adapter. We will also need at least one GE Multilin SR relay, a MultiNet unit and a multi-link switch, and Category 5 enhanced T100 base T straight-through Ethernet cables. The GE Multilin RS-485 ports support a protocol called Modbus, which we will discuss in detail later in the course. At this time, it is sufficient to say that the Modbus protocol is like a language and operates on a master and slave basis. Within the implementation of Modbus, there is only one master on the network and at least one or more devices acting as slaves. The master initiates all communications. The GE Multilin MultiNet Serial to Ethernet Converter is a communications module that interfaces an RS-485 Modbus LAN to an Ethernet LAN. This allows multiple Modbus masters on the Ethernet LAN to communicate to the slaves on the RS-485 Modbus LAN. The MultiNet does this by buffering the commands sent by the masters, and then acting as the master on the RS-485 LAN by repeating these commands to the slaves on the RS-485 LAN. Once the slaves respond, the MultiNet master sends the response back to the appropriate master on the Ethernet LAN. The MultiNet acts as a server on the Ethernet LAN and a master on the RS-485 LAN. We will assume that the RS-485 LAN has been wired to the slaves correctly, and each relay has been assigned a unique Modbus slave address in addition to matching baud rates and parity. We will focus on the configuration of the computer and the MultiNet. Let's start with the computer. The first step is to configure the computer's IP and subnet mask addresses. Without these addresses, a device cannot communicate over an Ethernet LAN. Within an office LAN, this configuration is normally performed automatically by other computers on the network called servers, which are running special software. Relying on a server to perform this function within a protective relaying LAN isn't desirable, as a failure of the server could result in failure of the entire Ethernet LAN. A provision is made within the computer to configure permanent, or what is termed static IP and subnet mask addresses, such that a server isn't required. Let's see how this configuration is performed. First, we need to obtain the IP, subnet mask, and possibly gateway addresses from the LAN administrator. There are rules associated with the assignment of these numbers which go well beyond the scope of this course. For all intents and purposes, this is just a method of identifying the specific devices on the network, which has no bearing on the protection and/or flex logic performance. For a test network which will allow 253 devices, you can select a network mask of 255.255.255.0 for all computers and relays. The IP address must, however, be unique. For the test network, IP addresses ranging from 3.94.244.1 through to 3.94.244.253 can be used. Once the computer has booted, right-click on the icon labeled My Network Places, followed by the Properties selection. Right-mouse-click on the Local Area Connections icon and select Properties. Locate and click on the Ethernet card. The Ethernet card is typically referred to as an Ethernet adapter. Select Use the following IP address, and then enter a unique IP address. We will enter an IP within the range of our test network addresses. Next, enter the subnet mask. We will enter our test network address. Next, select OK, and then OK again to exit the Local Area Network Properties menu. This should return you to the main Windows screen. Select Run, then enter CMD to start the DOS shell. At the DOS prompt, enter the command ipconfig/renew, followed by the Enter key. This is the command that will cause the Ethernet adapter to immediately use the Ethernet IP and subnet mask addresses we just programmed. An on-screen report will appear indicating which addresses are now being used by the adapter. Next, we will configure the MultiNet to act as a communication bridge between the RS-485 LAN and the Ethernet LAN. The MultiNet can be directly connected to a computer using a crossover cable, or via a switch using standard 10100 base T cable, which would allow additional computers or devices to communicate with the RS-485 network and each other. With either configuration, once the cable has been connected at both ends, a small LED called the link light should illuminate within a couple of minutes. This LED is typically located at the port. If the LED fails to illuminate, something is wrong. Usually a faulty cable is the cause. Check the connector and/or replace the cable and try again. Remember that it may take a couple of minutes after the connection for the link LED to come on. Once successfully connected, the MultiNet server can be configured through Ethernet using its Media Access Control address. This MAC address is unique in the world to this device and was assigned during manufacturing and cannot be changed. The MAC address is located on a label attached to the back of the MultiNet. To configure the MultiNet, launch its setup software, which can be found on the GE Multilin product CD or website. Enter the MAC address found on the MultiNet label, in addition to a unique IP address. We will enter an IP within the range of our test network addresses. Next, enter the subnet mask. Here we will enter our test network address. The gateway address would only be added if one existed. Next, enter the baud rate and parity setting of the RS-485 network, and then click on the Save button to save the settings to the MultiNet. If the settings were saved successfully, a message to that effect will appear. Once the settings have been saved to the MultiNet, click the Ping button to test the MultiNet's communication to the computer. A reply from the MultiNet confirms that the communications are working properly. The last step is to confirm communications to each SR relay. Launch the appropriate SR software and go to the Device Setup menu. Select Add Site, and then select Add Device. Set the interface to Ethernet. Enter the IP address of the MultiNet and the slave address of the SR relay. The order code and firmware version can be read from the relay itself to fill in the last two fields. Press the Read Order Code button. The appearance of the order code and firmware version verifies that the Ethernet communication link is working correctly. If not, check the RS-485 cabling, terminations, SR relay baud rate and parity, and once the problem is resolved, read the order code again to verify correct operation. Select OK to save the settings and exit the Device Setup menu. The SR relay can now be programmed or monitored via the Ethernet LAN. Note that if a second computer is connected to the Ethernet LAN, both computers can monitor or program the relay at the same time. Through the Ethernet LAN, the MultiNet takes the requests from both computers, which are Modbus masters, and then issues the commands onto the RS-485 LAN. The responses from the slaves on the RS-485 LAN are then passed on to the Ethernet LAN via the MultiNet. Now we will add a universal relay onto our Ethernet LAN. The physical configurations of the communication ports for the universal relay vary between the older version 3 CPU hardware and the more recent version 4 CPU. However, the functionality remains for the most part the same. Regardless of the version, the port located on the front of the relay is an RS-232 port with a default configuration that supports the point-to-point Modbus protocol, or can be configured to support DNP. This port cannot be networked when point-to-point Modbus is being supported. In addition to the front port, both versions 3 and 4 offer 3 different communication configurations. The first configuration being two RS-485 ports located on the rear of the CPU that can be configured to support Modbus RTU or the DNP protocol. The second configuration is a single 10 base T or F Ethernet port in addition to an RS-485 port. The Ethernet port supports UCA 2.0 and Modbus over TCP/IP. The third configuration is a redundant 10 base F Ethernet port. For this configuration, the relay typically uses the normal port for communication and will automatically switch to the alternate port if the relay detects a problem with the normal port. Once the normal port is healthy again, it will automatically switch back. Now we'll configure the UR. Using the keypad, enter a unique IP address and subnet mask. Again, if using our test network addresses, the unique IP address will be in the range of 3.94.244.001 through 3.94.244.254, and the subnet mask will be 255.255.255.0. Set the Modbus address and configure the Ethernet port for full duplex. Connect the UR to the switch via a 10 base T cable and ensure that all appropriate sync lights are lit. To test the network, perform the ping test as follows. Start the DOS shell on the computer by selecting Run, then typing CMD followed by the Enter key. Type the command ping followed by the appropriate IP address number for a specific UR. You should receive a response indicating successful communication. Next, unplug each individual UR and ping that UR's address again, and you should get a timeout response indicating that no other device on the LAN has this IP address. If you get a response other than a timeout, this means there is another device on the network with the same IP address. Since no two Ethernet devices on the same LAN can have the same IP address, you will need to correct this situation. Connect the cable and perform the ping test again to verify the UR is again communicating on the Ethernet LAN. Launch the EnerVista UR configuration software and select Device Setup. Enter the UR's IP and slave address and select Read Order Code. The appearance of the order code and firmware version verifies that the Ethernet communication link is working correctly. This concludes the 10100 base T lab. In power system applications where longer distances are involved, fiber optic Ethernet is preferred over the more popular 10100 base T LAN medium due to its immunity to EMI. The higher cost and difficulty of terminating fiber cables allows twisted pair to continue to be used where appropriate. Ethernet fiber optic LANs were first referred to as fiber optic inter-repeater links. The name was later changed to 10 base FL, FP, or FB, and then finally 10 base F. The original specifications for fiber optic Ethernet were based on the technology of the mid-80s calling for the use of multi-mode fiber with fairly limited distances of 2 kilometers or less. The need for full duplex communication over greater distances, at greater speeds, sparked research and development. The resulting improvements in the fiber optic cable, transmitter, and receiver technology enables users to create full duplex 100 megabit Ethernet networks that are fast, reliable over long distances, and fairly inexpensive to install and maintain. Inevitably, the question arises, what is the maximum practical communication distance for fiber optic cables? The answer isn't straightforward, but must be calculated. First, we must understand that as the light travels from the transmitter to the receiver, the light's intensity is attenuated. Attenuation is measured in decibels and can be considered as the decrease of signal strength as it travels through the light path or medium. If the intensity of the light is too low, the receiver will not be able to detect the signal. The maximum distance is calculated in the following way. First, the power budget is determined by subtracting the transmitter's rated power from the receiver's sensitivity, both of which are measured in decibels of light intensity. For example, if a particular transmitter is rated at minus 15 decibels and the receiver's sensitivity is rated at minus 35 decibels, the difference of minus 20 decibels is the power budget. The power budget can be thought of as the maximum permitted attenuation of the light signal as it travels from the transmitter to the receiver while still permitting reliable communication. The next step is to calculate the total expected attenuation of the light by summing all sources of attenuation such as the cable, connections, splices, etc. as follows. Take the cable's rated loss per kilometer, which is in the order of minus 0.35 to minus 3 dB per kilometer depending on the cable type, times the cable length. The result is the total loss due to the cable. Next, we add the losses through the cable terminations, which is minus 1 decibel per termination point. If there are any cable splices, the attenuation per cable splice must also be added to this total. Minus 3 decibels is added to account for cable aging, and finally, an additional minus 2 decibels is added as a standard safety operating margin. It's important to note that at one point in time, some areas of Europe used non-standard 50 by 125 micrometer instead of 62.5 by 125 micrometer fiber. If sections of this cable is being used, an additional minus 3 decibels is added for each section. The sum of all these sources of attenuation is the expected total attenuation. The power budget is then compared to this total attenuation. If the power budget is greater than the total attenuation, the link will be able to provide reliable communication over the given distance. If not, the link will require modification to lower the total attenuation. Common actions to reduce the total attenuation include the use of a cable with a lower attenuation per unit distance, or the installation of a fiber optic repeater to boost the signal strength. There are two types of fiber optic cable in use today: multimode and single-mode fiber optic cable. Multimode fiber is constructed such that for a given wavelength of light, the index of refraction at the surface is so high that there is total internal reflection. This can be imagined as the fiber optic cable being a tube whose interior surface is polished so smooth as to be like a mirror. Then imagine that the transmitter is like a light shining at one end of the tube. Some of the light will travel straight down the tube, while some of the light will reflect off the walls of the tube's inner mirrored surface as it travels along the tube. Single-mode fiber's construction is such that it acts as an elongated lens that is continuously focusing the light into the center of the fiber. Using these two analogies, it can be imagined that light traveling through a single-mode fiber travels through far less fiber medium, resulting in far less attenuation per unit distance than does the light traveling through a multimode fiber. As a result, for a given wavelength of light, single-mode fiber typically has less attenuation per unit distance than a multimode fiber. The wavelengths of light that are used in fiber optic communication are 820, 1300, and 1550 nanometers, because it's been found that these wavelengths of light are attenuated less than other wavelengths of light as they travel through the fiber optic medium. Traditionally, 820 nanometer cable has been offered only in multimode, but recently single-mode 820 nanometer cables have come into existence. 1300 nanometer cable is offered in both single and multimode, while 1550 nanometer cable is typically only offered in single mode. Let's take a closer look at the construction of multimode and single-mode fibers. The outer clad of both is 125 micrometers in diameter. The multimode core at 62.5 micrometers is a little bit thinner than the average human hair. Single-mode fiber is also referred to as 9 by 125 micrometer fiber. The 9 refers to the 8 micrometer core in addition to a second outer clad which can pass a light signal. The 125 refers to the outer diameter of the fiber. There are several types of connectors that are attached to the end of the fiber cable to allow for the connection of the fiber to other devices. The ST connector is very robust and popular, and for these reasons, this style of connector is used on both the GE Multilin Universal Relay and the F485 converter. Now we will switch the UR on our Ethernet LAN to a fiber communication link. It is desirable to use a fiber optic link whenever possible due to its immunity to electromagnetic interference. To convert the existing 10 base T connection between the universal relay and the switch to a fiber optic link, the student need only replace the 10 base T cable with an 820 nanometer multimode fiber optic cable. We will connect the fiber optic transmit port of the relay to the switch's receive port, and vice versa. Remember that the maximum distance of the fiber optic cable is defined by the power budget minus the attenuation. Therefore, it is important to note that the universal relay has a 10 dB power budget. Unlike 10100 base T, the fiber optic ports do not auto-negotiate the baud rate. This is because the 10 base F ports use 820 nanometer light, while 100 base F ports use 1300 nanometer light. Due to the difference in the light frequency, 10 megabit ports cannot communicate with 100 megabit ports. We must verify that the baud rate of each fiber optic port matches before making any connections. Once the two are connected, we ensure that the link LED illuminates on the MultiNet. Now we have successfully switched our UARS communication link to fiber.